In this video, we are going to wrap up this section talking about simple harmonic motion and dampened harmonic motion. So what harmonic motion is a motion that will continue forever. Usually involves a restoring force. So when the object isn't disturbed, it will go and keep going and going. So one thing we like to look at typically in physics to study this is a pendulum, or it could be a spring that's a weight's hanging from a spring and we let it go. We've seen a problem like that in our videos. But if it's at rest, it's at equilibrium. Usually the force that pulls on things typically would be friction, stuff like that. That's the dampening forces, the thing that we're going to talk about here in a moment. But these simple harmonic motion will assume that there is no kind of force on the spring or a pendulum that would stop it, meaning it would go on and on forever. And we can see this if we think about our functions being represented with a sine and cosine function, right? It's going to bounce back and forth, but it never actually stops like a pendulum. It's supposed to swing back and forth, but we know that eventually it should stop. Same thing with the spring. Being pulled down on a weight, it'll bounce for a while. If we were to use these functions, that's assuming that it'll never stop. We will take a look at a dampening factor in the second problem of this video. So they're going to give us a simple harmonic motion problem here. They want us to find the displacement of the object. So if we want to know how far is it changing, well, that's going to be 2 times our amplitude. All right, so 2 times our amplitude would be the actual displacement covered. Well, that would be 2, in this case, 5 times 5, so our displacement would be 10 units, whatever we're talking about in this case. Our period for a harmonic function is the same thing that we've dealt with in the past with sine. It's going to be 2 pi over, and in this case, it's omega. That omega is b. It's the same thing. They just put a new letter on it. 2 pi over 3. Okay, that's our period. And then we have a new term here. Frequency is how many times will it go through its cycle in 1 unit measure. So if we were talking about hours, it'd be like how many times does a pendulum go through its full cycle in 1 hour, right? Or if we're talking about a spring, it would be how many times does it go back and cover its full period in 1 unit of time. So how we actually do that was up here. We kind of passed over it. It is omega over 2 pi or b over 2 pi, same thing. So it would be omega over 2 pi, and that's going to be, our omega in this case was a 3 over 2 pi, and then we could actually just get a decimal here. Let's go ahead and do that. So 3 divided by, make sure you put 2 pi in parentheses so your calculator doesn't multiply by the pi. So it goes through about 4.775 cycles in 1 unit of measure. So per cycles in 1 unit, let's put time per t, right? Whatever we're talking about, they didn't give that to us. They also want us to sketch it here, so we'd use this exact same information, just like we have in the past. This is 2 pi over 3. To cut 2 pi over 3, I want you to take a look at this. If I cut 1/2 and a half, I get 1/4. If I cut 1/4 and 1/2, I get 1/8. And if I keep going, I just cut it in half. That same thing's happening when I divide fractions. So if I had 2/3 to cut it in half, it'd become 2/6. To cut that in half, it becomes 2/12. I just double the denominator, and it cuts my fraction in half. So this is actually 2 pi over 6. And I know that goes down to pi over 3, but I'm just going to leave it. Cut that half. Well, 2 of anything, I cut it in half, I get 1 of them. And then I'm counting by 6, so this is going to be 3 pi over 6, or I could call it pi over 2, but I'm going to leave it that way. The amplitude was 2 in each direction, so I'm going to have a 2 and a negative 2. And then we're dealing with sine, so I'm going to put sine right on the midline and run right through my pattern. I know we're going pretty quick, but this should all be review. It just applies when I'm talking about motion as well. That's the whole point that we're studying these, is to apply it to the real world. All right, well, the reality is, dealing with harmonic functions, is there some kind of dampening force or some kind of restoring force. In most cases, it is friction that is slowing forces down. In our spring problem, it would be forces. The forces applied would be our friction and our gravity, stuff like that. So we call this damped harmonic motion. And this is more of a realistic, and you guys will do more realistic harmonic motions when you guys get to DiffEq, differential equations. But this damped harmonic motion is taking in some kind of factor that it is getting slowed down by friction or by gravity, anything like that. So these functions are represented with our e function, e to the negative, and we put some kind of c, so dampening factor. And if I take e to some negative number, what happens is I flip it over and it's 1 over e to the 5th. Remember, e is just a number, so what we're doing when you get bigger is as that c gets bigger, the dampening factor, we're multiplying by a smaller number, which is slowing it down faster. And then we put a t on there, like negative 5 to the t, then that number here in the exponent, gets bigger and bigger, or more and more negative, flipping it over 1 over e to the 5t, and then the big T getting bigger and bigger makes it smaller and smaller. So even though our sine function is going up and down, over time it's going less and less because that dampening factor is making it smaller and smaller, like reality. So C is our dampening factor. A, the amplitude, right, of our function, if we see that, the amplitude not with the E, is our initial displacement. It's going to be different now because we don't have a solid amplitude. Right? It is actually getting smaller every time. So this whole E, but we have an initial amplitude. That's why it's called initial displacement. And then our normal for the period, and then frequency is also the same that we just learned, omega over 2 pi. Okay, so here's an example of this. They're just going to give us information and have us put it where it goes in the formula. So a spring oscillates with a frequency of 4 cycles per second. So I have F equals 4. And this is going to be cycles per second. Its initial displacement is 2 centimeters. We figured out that that's just our initial amplitude. And then they gave me the dampening factor, which is 0.65. This would be a rate found by an experimental observation, finding that given data points. Okay, given the function f of t that describes the position of spring t seconds. So we just have to come up with a function. First thing I'm looking at is I need an a, I need a c. Okay, I got a, I have c, I need an omega. So the frequency definition is omega over 2 pi. And I'm going to replace that with 4 equals omega over 2 pi, and then we're going to solve for omega. So omega is, multiplying both sides by 2 pi is 8 pi. So this gives me everything I need to plug into my function. These are, I think, deceptively easier than they look. Typically, most people are very intimidated by these problems. Just slow down and make sure you find each bit, and most of these are given formula-wise to us. Right, so I plug everything in. My A is 2 times e to the 0.65, and there's a minus, 65t times sine of 8 pi x, or t rather. So there it is. And they didn't ask us to plug anything in. Sometimes they'll ask us to plug some data points in, like how, where's the spring out in 3 seconds, or what time would it happen? And we're just plugging in different values either for the left side or the right side of our equation. So these will feel maybe new, like you've never seen them, but they're just an application of the first handful of sections for this chapter.